So the idea is that, the scalar is the real weird thing actually. Gravity and electromagnetism are fine in some sense. But if you fix the scalar to an arbitrary value at the boundary, it doesn't have a good asymptotic limit. Because if you take the solution which ends at some finite phi naught at the boundary, let's say, if the scalar field solution that fixes at phi naught at some point, and if you take it all the way to infinity, there is no good solution because of no Hare theorems. Sure. Sure. What is the Cauchy variation problem? Right. Yeah, but that's the standard thing that you also have in ADS, right? I mean, but the idea of having a reflecting boundary condition is that this effectively becomes globally hyperbolic. Right, but I'm saying that, so that notion depends on the definition of a well-defined notion of an energy that exists in ADS. That's a generalization of ADM. And what I'm saying is that sort of a definition is, I don't think that when you fix the F phi naught at the boundary, I don't think it is known, but I think it should exist. Yeah. Okay. Yeah. I think that's kind of like a Cauchy data problem with a boundary, right? I mean, I think it's a complicated partial differential equation question. I mean, but I think it should have a good answer. No, I don't know, but I think that it should. Because, see, the couple of reasons why I think that. Because when we do this, the results that we get are extremely reasonable. Like what we find is essentially the same phase diagram that we find in ADS, for instance. So, and that's one reason. And there is a sociological reason also, because Brown and York, who are, who know general relativity and boundary terms better than anybody else, believe that this is okay. Yeah, so I'm right. I mean, but that is but that problem is always there, right? I mean, in the sense that what can happen when you say that you have GR with a fixed boundary condition, boundary metric, then you're already restricting it in some ways. Because, for instance, what I'm basically saying is that, like, typically the standard statement is that in GR you have, you take a manifold and then look at metrics which solve Einstein's equation. But in practice, that's not what we do. That's true. But this has nothing to do with my talk, by the way. I'm just saying. Yeah, I mean, not all initial data are clearly not acceptable. But I think that, no, not all. So you're worried that some sort of anisotropy might completely destroy everything. This I don't have an answer, but I don't think it does. Because, I mean, well, it might happen. Like, first of all, if you're looking at static spherically symmetric solutions like we are doing, I don't think it matters. Also, another thing is that for curl-like solutions, also Brown and York consider similar things, and there also it seems to be fine. So that's not quite anisotropic in a real sense, but still at least, it has actual symmetry and so on, but it seems to be acceptable. Well, I mean, yeah, I mean, that is probably, settling for too less. I think that it might not be a real problem, but I don't want to say too strong statements here. Okay, anyway, so now onward to my talk, which is that, so the picture is basically that you have a metric, you have a manifold with a fixed boundary, and that's how you typically define gravity, okay? So, and let me just draw a quick picture here. This is our space-time, this is the boundary, and we would like to have this to be a well-defined problem, well-defined variational problem. Or if you want to think of it in terms of saddles or something, you can think of it that way as well. So what I'll talk about today is instead of fixing this G, this makes the gravity as a Dirichlet problem well defined. But instead what I would like to talk about is that is it possible to have like something analogous. In scalar field theory, for instance, you can either put phi fixed at the boundary or you can have phi prime fixed at the boundary, the normal derivative of phi fixed at the boundary. So it's not known, I mean, despite a lot of Googling that we have done and talking to various people, we have not found a real Neumann way of formulating gravity. And I would like to say that, so what we are trying to do here is to slightly change the problem in a hopefully very minor way, and then offer a solution to this Neumann problem for gravity. Okay, so that's basically the starting point. So I'll just start with particle mechanics, as we always do. So I'll call this is P and this is D, and D stands for Dirichlet. So what I mean by Dirichlet action for a particle, P is particle, is that I look at some action of this form. I can also have a lower boundary for this T, but I only care about one boundary, which is enough for my purposes. So the point is that, so this, I call it Dirichlet, but it's not really Dirichlet. What we typically do is we fix Q at both the beginning and end of the time interval. So it's not technically Dirichlet because it's usually like a boundary statement, but instead I'm using the word Dirichlet to talk about fixing things at the time direction. But that's the same sort of thing will be what we'll use the same sort of thing for gravity as well. So the variation of this, I'll just do this in a little bit of detail so that I can just write down the answer in the gravity case. So this gives me, assuming I have not made a mistake, plus other boundary. So this is the standard thing. I'm just splitting it into the variation to this. And the claim, because now the point is that delta Q shows up on the boundaries, you can fix Q to be any fixed value, and then you have a well-defined variational problem which gives you the standard equation of motion. So this is standard thing everybody knows. So we'll write it in a slightly different way, so what we want to do is we can have, but this is the typical Dirichlet problem of particle mechanics. But we can also have a Neumann problem of particle mechanics, which is that instead of fixing Q dot at the initial, Q at the two boundaries at the time limits, we would like to have a problem where it is the Q dot that is getting fixed at the two ends. And the way to do that is just to add a term. So I'll call this my Neumann particle action, which is just to take this minus this. So this is very simple. And in the case of, you can see that when you go to field theory, instead of having it at one value at a fixed time here, you'll have an integral on the boundary. So that's what we're going to have. So now the variation of this guy basically gives us delta Q dot, so which means that I can take Q dot to be any fixed thing at the at the boundary, and then I have a well-defined variation problem. So this is basically the Neumann version of particle mechanics, which is trivial, but so this is what we'll generalize. Okay. So it turns out that immediately doing this based on the derivatives of the metric for gravity doesn't really work, because metric derivatives are Einstein's action is complicated and it has a specific structure. And it doesn't immediately lead to any kind of good Neumann problem for gravity. So instead, what we'll do is we'll start with particle mechanics, but in a slightly more Hamiltonian-like setup. So we'll notice that this, at some fixed t, is phi t, where this is, I'm taking a boundary I make this observation, it's trivial, which is that I'm just defining a canonical boundary momentum, which is just the boundary variation, boundary derivative with respect to Q of my Dirichlet action. So now I can think of this term as this. Okay. So this is the way in which, so the advantage of that in the classical mechanics case is essentially it just seems like the same thing. But in the case of gravity, it turns out that this leads to a major simplification. So in particle mechanics, fixing pi t, at the boundary is fixing pi t at the boundary is really the same thing as fixing q dot. But in the case of gravity, this leads to a major simplification. That's the point. So that's what we'll call our Neumann problem, even if it is a slight modification. Sorry. I meant this. Is that correct? This is okay? Yeah. So this is what I meant. So I can fix my pi t at the boundary, and then it's done. Yeah, that's true. Pi t, yeah. Yeah, that was a mistake here. Okay, so my Neumann action now in this kind of notation, it basically looks like this. It's just that I have times qt. Okay, so it's basically some sort of a boundary legendary transform, and that's the form that we'll try to generalize. Yeah. It's basically the boundary is stress tensor density. So that's what we will hold fixed. So I'll write that down. So the precise places where we define the boundary, it's a little bit like, for instance, even for Gibbons-Hawking, whether you take it as an initial value problem or a boundary value problem is, it's somewhat up to you and depends on the problem that you're considering. So initial value, let me answer that question later. Maybe, I don't think I have an answer, but maybe I, yeah. Mm-hmm. That's right. That's right. No. So when I was talking about Brown-York, I was talking about their quasi-local definition for the stress tensor. I wasn't really talking about, they don't have a specific, so the boundary term that really, there's only one boundary term. That is, there are some, very, very specialized cases that people write down sometimes. But the only real boundary term that people use in gravity is Gibbons-Hawking and York. Gibbons-Hawking-York bonds. No. That boundary term, definitely you have to fix the boundary metric. So if you fix the boundary metric, then it gives you a well-defined variation problem. I'll show that. I'll write down the variation of Einstein-Hilbert plus, this thing. So the standard Einstein-Hilbert is this. Yeah, so maybe I should go through that in some detail. So let's say this. And the point is that the variation of this and if there is any mistake here, I think Avinash or one of those can correct me. So this is so H is my induced metric on the boundary. I'll just I'll work with time-like boundary. So there is, in principle, I can put an epsilon and work with both space-like and time-like guys. I'll just look at this. And then you get, so this is the variation of the Einstein-Hilbert piece. And what Gibbons-Hawking term does is that, so I'll write that down. So here you can see that, because of these two separate terms that show up here, just fixing the boundary metric is not enough to give you a well-defined variation problem. what Gibbons and Hawking do is they add this. This to that, and the variation of this is precisely such that you get so the equation of motion piece, which I won't write again. This is the boundary piece that comes out of it. So because this boundary piece, if you fix now this boundary metric, the induced metric on the boundary, then you have a well-defined variation problem. And this is the reason why, yeah, that metric can be absolutely anything. And that's important. That's important because the full space of solutions. That's right. Because the equations of motion are coming from here. So anything that solves this, as long as it satisfies whatever boundary data that you put here, then it will give you the same class of solutions. But the thing I want to emphasize is that the reason why this is an interesting boundary term, and many times in most of the papers that, many people who have asked us for citations when we put this out, many of those papers, what they really do is that they have a specific boundary, specific geometry of the boundary, and on specific boundaries you can have specific boundary terms. You know what I'm saying? Like for instance, one of the things that many times people consider is things of this nature on the boundary. But this is not saying that Kij is fixed at the boundary. This is saying that Kij is some specific quantity equal to 0. So this is a differential constraint on the boundary surface. So that means that the boundary surface has it's not generic. Here on the other hand, the Gibbons-Hawking, the greatest thing about it is that it's a generic boundary surface. For any boundary, you can do it. So yeah, and that's basically that. So you hold your boundary induced metric fixed, and then your variational problem is well defined, and that's that's the Dirichlet problem. So we'll call this as the Dirichlet action for gravity. Okay, so this is the standard one everybody uses. Matter you can in principle add, depending on what you want. It's an independent boundary piece, right? So you can add boundary terms specifically for the kind of boundary condition that you put on matter. Yeah, so there might be some concern, but this is not something we have really explored. Okay, so but I'll just be talking about gravity. I won't really talk about it. Okay. So, but the point is, this is the only boundary term that has been written down, for a generic surface for 40 years. But we can do the same thing that we did here for the case of gravity. And so this object is basically our Phi-ij. Okay. So this object, let me just write it. Phi-ij is delta SD This is my canonical boundary momentum. And using the same sort of thing that I did there, so now what I can do is I can see that this plus SD minus, I can So it depends on where the boundary is. Yeah, this is true in the sense that, for instance, when I talked about Qt here, I am also taking a variation in the this is not really a Dirichlet problem. For instance, this is a problem in the time direction. So I'm just saying roughly, I'm just saying that it is boundary, the canonical conjugate in the boundary direction. So that's all I'm saying. So yeah, so this is essentially the stress tensor density if you're familiar with the ADS type of stuff. So yeah, so this is one way to write this Neumann guy. So this object, so now I can write it in a slightly nicer way. by knowing that pi ij has that form, so I have an action so let me write down the Dirichlet action first, just for comparison. So this gives me S Einstein-Hilbert plus Neumann going to be it's again an extrinsic curvature type term. So this is the action. So this piece is dimension dependent, and that's what will give some interesting whatever. Very simple, and so that's basically the action. Any questions before I make some comments about it? So I started with, so this is my Dirichlet action, and the point is that by doing an analog of what I did here to go from Dirichlet to Neumann, I can just subtract a piece of the same form here, and I know what pi ij is, so that gives me this, and if you plug it in, and this is the Dirichlet action which contains both these guys, and I just do a simple algebra and I get that. So that's it. Here is again the extrinsic curvature. So this piece, this and this are really the same. But the coefficient is different, and now if you vary this, you won't be able to do hij fixed at the boundary, because hij is no longer fixed. Because yeah, that's the point. So you have to. So the analog of it's in some sense, yeah, the variation problem with the boundary fixed at the boundary metric fixed is no longer a well-defined problem. So on the other hand, this pi ij that I defined is a well-defined quantity, and so one of the reasons why we were interested in this, because when you go to ADS, for instance, fixing the boundary stress tensor, instead of fixing the metric fixed, you can try to fix the boundary stress tensor fixed. And in the ADS case, what you find is that the natural thing to fix analogous to this is the renormalized boundary stress tensor. And when you do that, you find that you can actually get a finite action and finite counter terms, new counter terms and all that. So that is one reason why we, in some sense came to it. So yeah. So I mean, yeah, that's it. So you can see some curiosities already, like in d equals 4, for instance, this term is not there, which basically means that for standard Einstein gravity has a formulation. It can be thought of as a Neumann problem, even without any boundary terms. So, and after our paper came out, there was some references which kind of had casually observed it in some places. Yeah, so I think the point is that it can also be in principle be space-like, because this is just, it's as general as Gibbons Hawking, in the sense that you can do, as long as this object is well defined, and which only basically is reliant on the fact that your boundary is not null. And I mean, maybe there are generalizations also null, but so that's the only thing that it depends on. So in that sense, it is really like you could do the same sort of things. So I didn't hear the conjecture. What is the conjecture? Yeah. So yeah, I mean, I don't know much, but I'll just say that fixing the extrinsic curvature on a surface is to be anything. If it is a given extrinsic curvature, you can't put that on an arbitrary surface. Yeah. Yeah, then I think it would automatically evolve it to the new slice. I mean, I think it is. Yeah, it should be. I mean, it seems like kind of a reasonable. Yeah, I mean, I don't know. So yeah, also it's not quite the extrinsic curvature that we are fixing, it is that specific combination. So that also is somewhat important. So okay, so that's one. So in for d equal 4, you see that there is no boundary term, and also in d equals 3, it basically reduces to a half of the Gibbons-Hawking term, which in the ADS context people had looked at because it translates. So one thing you can check is that in d equals 3, at least for in the ADS case, this can be translated to a standard, so just the Chern-Simons theory with no extra boundary terms at all. So that's one more point. Yeah, so this is something I already said, which is that if you fix Kij, fixing Kij arbitrarily is not always a viable thing to do because your surface is might not allow it. Okay, so this is, I did this in some detail because this is the part which is easiest to do. So the rest of the thing, I'll kind of be somewhat sketchy. You can look at papers that should come out in the near future. So one of the things that you can do is you can do a Hamiltonian version of, you can look at the Hamiltonian action version of this action, and yeah. That's right. Yeah. So I mean, wherever you have boundaries, you always have the choice of either putting this or Gibbons-Hawking. For instance, at the even in a geometry where you have asymptotically, you might put these Neumann boundary conditions. I still think that at near the horizon, for instance, the Hamiltonian type of thing that Gibbons-Hawking used to compute the entropy, I think the natural thing to put is still the Dirichlet boundary. So there, when you have when you add a boundary piece, it should still be Dirichlet. Does that make sense? In the sense that, like, when you split your geometry into this type of thing, you can put whatever boundary condition you want here. But here also in the Hamiltonian setup, there is a boundary piece that you will add. I mean, boundary piece in the sense it breaks down into a, so there is an type of piece, right, that you add at the surface. So that piece, this is really just the Gibbons-Hawking term of this point. And I'm saying that I think still should be the same, because that's like the most natural thing in some sense, because you want some sort of fixed metric at that point. And it's, it also gives you the right entropy. But yeah, so a couple of things. One is that we can write down the Hamiltonian, ADM split of this action, and the Dirichlet action basically takes this split. Which we saw today morning, something like this, plus this is the rough structure. So I mean, there are explicit expressions you can write for n. So here, what I'm doing is I'm doing an ADM split of the metric, and then writing it in terms of the canonical conjugate of HAB and so on. This is a standard Hamiltonian version of writing it, and if you include also the Gibbons-Hawking piece, the final expression takes this form. Okay, so this epsilon and JA you can define in terms of extrinsic curvatures and things like that. So that's the boundary. So this has an interpretation in terms of epsilon and JA, and so a similar thing that you can do here gives you the same bulk piece, but in the boundary, it ends up giving you So here you see that this is the spatial part of the boundary metric. So the spatial part of this is, in some sense, like if you think of N and NA as canonical conjugates of this epsilon and JA, so this SAB is the canonical conjugate of the fixed spatial part of the boundary metric. So this is the structure that we get. And the reason why that is interesting is because one way in which you can motivate thermodynamics for black holes, so let me just repeat for the students in the audience how the original computation of Gibbons and Hawking to get the thermodynamics of the thermodynamics of black holes by looking at actions, saddles of the Euclidean path integral. So the basic idea is the Dirichlet action, which is basically just Einstein-Hilbert plus the Gibbons-Hawking term that I wrote down. This is, they set this equal to this. Well, I mean, we don't have to necessarily put this, so we'll just keep this guy. Okay. So the Dirichlet action is the one that we had with the Gibbons-Hawking term, and if you add this piece here, this you can compute covariantly. And the way you compute it covariantly is that you subtract the background, you do a background subtraction for the extrinsic curvature piece, and then you get a finite answer for this, okay, in flat space. You can do also, we have done this also for radius. I'm just telling you the general story rather than dwelling on the details. So this is, so you subtract it for the, so once you have the subtraction done, this gives you a finite answer, and the finite answer for the case of, flat space takes this form for curved black holes. Or, yeah, let me just put this guy also. So this is the result of an explicit evaluation in the covariant form. Okay. So what Gibbons and Hawking do is that they just set these two guys equal to each other, and then they see that this gives rise to a smart form. So this is something that is already known from classical GR, and so then you can say that, okay, the right hand side, this is the expectation that, setting this equal to this was just coming from, the saddle of the path integral, right? So this is just the free energy, effectively. So the free energy, you set this equal to what you expect from thermodynamics, and then, and that comes from the saddle of the path integral, and then you explicitly evaluate this ST by background subtraction, you get some answer, you equate these two expressions, and you get a smart form. And that's the way in which, this entropy, if you want, is motivated in the standard Euclidean path integral in this sort of Gibbons-Hawking type ensemble. So what we can do is, so one observation. So this, in the original Gibbons-Hawking paper, they just take this to be a given. So because of the, this E minus Ts minus mu q is a thing that you expect just based on the fact that you understand your ensemble to be canonical. So we don't have a good ensemble description yet. We don't really understand what exactly this ensemble is. But one way in which we can proceed, kind of by analogy, is that here, this right-hand side that we have, this object that we have here, that Gibbons and Hawking just take it from, just from thermodynamical arguments, you can actually get the same expression by looking at the Dirichlet action on that cigar geometry that I told you about. So each of these pieces, so this will be a piece coming from near the horizon, and each of these pieces just directly show up from these two boundary pieces that you have. Okay, so in a sense, the thermodynamics comes from comparing the covariant and the canonical versions of the Dirichlet action. So we can try doing something similar, even though the interpretation is less clear in our case, obviously. And what we find, so I'll write an expression like this. So I'll write this expression. So we have a Neumann action. Again, it is in flat space, we can do a background subtraction. Again, the background subtraction just means, again, you subtract k minus k naught, you have this 4 minus b factor, etc., hanging out there. And at the end of it, you get some expression. So this is the right-hand side that comes from all of these guys, or the flat space black holes is of this form. So this is the form that you get for the right-hand side from the Hamiltonian picture. And it turns out that if you explicitly, so again, this Sn can be explicitly evaluated, okay? And if you evaluate that, you find it, the value of that object is precisely such that at the end you again get the smart formula out of it. So, yeah, so I mean, maybe it is an argument that there is some ensemble which you should consider for the Neumann, which we don't fully understand. And the one reason I'm not really, I don't know exactly what, I don't want to talk too much about that ensemble is because I think this is a much more covariant way of looking at it. And this covariant way of writing the action is possibly more useful in maybe working with ADS, CFT, and so on. So, but yeah, if you compare the Hamiltonian and the covariant ways of looking at this action, you get thermodynamic relations which agree with the standard smart form. I mean, but the boundary stress tensor density is what we are holding fixed, right? So the way in which it works is that typically what we do is, even in the Gibbons-Hawking case, what we do is you look at a solution and then, fix the metric that comes out of it to be the fixed metric at the boundary. Here what we are saying is that for a given solution, again, we can evaluate what that TAB is, and then we say that, okay, that is the thing that we are actually holding fixed. And then the answer that you get, yeah, something like that, yeah. Well, I mean, it's not, I would say, so if you had T mu nu boundary stress tensor integrated to be finite, then it's a fixed energy ensemble, right? It's not so if the integral of T mu nu in some time-like direction integrated at the boundary, so this is somehow, it's a little bit like a microcanonical ensemble. No. This guy has all the components that you see typically in T mu nu. This is exactly the same thing. I just wrote it as Ij because, just because. So I mean, it's this, whatever the boundary directions, Hij has boundary directions in time direction also, right? So if you have a time-like boundary like this, so then it has components this way as well. So and then what you get is, this also has the same direction. I mean, it's the same thing as T mu nu. Absolutely. Yeah. So yeah, so what we have is, yeah, so you're right in the sense that what is the full meaning of, so if you just wanted a microcanonical ensemble, what you should really look at is pick some time slice. And so this is something that was done long ago by Brown and York in another paper, which is that, so this is, if you look at this is the Gibbons-Hawking action, Gibbons-Hawking version of Einstein action. And you can do, basically you do, you add a term which kills off not the covariant version of this, but just these two pieces that are here, so that what you end up with is just the bulk part of the action. And that's what they call the microcanonical action. Okay? So the microcanonical action is basically just, essentially what you're doing is you're holding epsilon and J fixed at the boundary. So that's not what we are doing. We are doing something more. So this is, yeah, so that's why it is, this, initially we were thinking that maybe, yeah, clearly they're related, but it's not super clear to us how exactly. Yeah, so this, if you want to hold these two guys fixed, which I think is the most natural definition for it's not quite a microcanonical also because it's the integral of these guys which will be fixed from the CFT point of view if you really want a microcanonical description. But if it is the energy density at the boundary is held fixed, energy and current density at the boundary is held fixed, then the microcanonical action will just be this. It's a boundary energy density. Right. That's right. But that's, so that's what I told, what I'm saying there is is not what this is. Here, this, you can do a Legendre transform only on these two guys, and epsilon and J, and then you can go to the microcanonical ensemble. Microcanonical again within quotes because it's densities that are being held fixed. But, so that is the thing that, that really is, I think it is really much closer to microcanonical ensemble than what we are doing. But ours is some sort of a strange ensemble, and it seems to have some sort of a, interpretation as a thermodynamic system because you get by analogy with working with Gibbons-Hawking, you get the smart formula again, but in a different way. So the precise way in which the formula is reproduced, I haven't shown you, but it comes up in a different way. So that's that. No, Einstein-Hilbert theorem is the only thing that is left. The boundary term vanishes. So essentially what you end up finding is that this left-hand side vanishes. But that is precisely the right thing that you require in order to get you the smart form. So yeah, so just in 4 dimensions. But in all dimensions this thing works. So I have 23 seconds. So I'll just say a few things about, just a couple of comments about ADS. So in ADS, yeah, I sort of mentioned it, which is that what we'll try to do is, yeah, I'll just say in words. So what we are, the analog of what we have done here is we can try to hold the stress tensor density fixed. I mean, the renormalized stress tensor density fixed, and then again, you have a well-defined variational problem. You can write down new renormalized actions. So I'll just write down the case for d equals 4, which is kind of a nice one. So d4x so this action has basically the property that what we are holding fixed is basically the renormalized energy stress tensor of Balasubramanian, Krauss, or Skenderis, or any of those people, and that's what we are really holding fixed here. But it also has a property that the action is finite. And again, we can check that this action, it's in a more subtle way than what I have shown here for flat space, and you don't need background subtraction because now the action is finite. You see that the Neumann action again gives you the thermodynamic relation. If you by comparing the canonical and the covariant ways of defining this, you find that again you get an equation of this form, which is again the smart formula for black hole. So I think I'll stop there. So it's also a coincidence, which is that in the Neumann action and the Dirichlet action both give you the same numerical value of the action in ADS for the various solutions. Thank you.